In this series of videos, I'm going to give lectures on general relativity. Now, I myself am studying this course in depth, and so I thought, why not take you all with me along this beautiful journey of general relativity. Now, for my reference, I'll be following the book by Sean Carroll's Spacetime and Geometry, right? And it's an introduction to general relativity, and there are lots of reasons to like this book. One of which is I love the way the topics are sequenced in this book. Now, some of the things that I'll be talking about in these videos will not necessarily be in that book, as I will be referring to various books for the course. So, now to start with, we are going to start first lecture on general relativity, and it's going to be on some of the tools that are required to understand general relativity, and we will be using these tools later on. Now, first of which is symmetry, and we will talk about vectors, dual vectors, tensors, types of tensors, and so on. And in fact, we will actually really see what vectors are and what tensors are. So you might think you know what vectors and tensors are, but you will be shocked when we talk about them, right? Now, let's start with relativity itself, right? So what is relativity, right? Well, when you say that the laws of physics take the same form to all the observers in an inertial frame, right? An inertial frame over here is a frame that's non-accelerating, right? That's what an inertial frame is. Now we are going to define some of the terms which we will be using in the lecture and in lectures that will come forward. And these terms are very useful as well. And so let's start with the first one, that is called the isotropy of space. And we will be needing these terms because we are talking about symmetry, right? Now, you will see what I mean. Now, isotropy of space is, say if you take your lab and you rotate it by any degrees, right? And nothing appears to change. Nothing changes, everything is the same. That's when you say that there is an isotropy of space. So I'll write some of these definitions down. So if we take our lab, so lab is your frame of reference, and rotate it, but nothing changes. Okay, and so that's what you call the isotropy of space. Now, there's another one that's called the homogeneity of space. So let me write it down. I don't know if I'll spell this right, but here it goes. Okay, of space. Right, and now here you say that you take your lab, right, and you translate it and nothing changes. by translation, you move it along a line and everything appears to be the same. That's called the homogeneity of space. So if we take lab and translate it, but everything is the same. So, but nothing changes. This is called the homogeneity of space. And finally, we have another one that's called the homogeneity of time. And this one is again pretty straightforward. Let me write this down. Yeah. This means that you have the laws of physics. Now, the laws of physics, they do not care about today, yesterday, or tomorrow. So, laws of physics do not care what time is it. They're always going to remain the same. So, it doesn't matter if you perform an experiment today or if you perform that experiment millions of years from today. The physics, the laws of physics of the experiment will not change, right? That's what homogeneity of time means. So the laws of physics do not care about time, right? And that's the homogeneity of time. Now here I have been mentioning lab, right? Lab literally means that it's any physical thing that can influence an experiment, right? That's what I mean by lab in these definitions. Now, there are two viewpoints for this. One is of Galileo, right? And the other one is of Einstein, right? Now, in Galileo's point of view, we have absolute time. And you might know all these things if you have studied special relativity in depth, right? And in Einstein's point of view, we have constant speed of light, right? So I'm pretty sure you know this, right? Now, of course, it turns out that these two are incompatible, right? So one of them has to be false. And it turns out that the constant speed of light is how nature works. And then the constant speed of light implies the homogeneity and isotropy of space-time, right? Now, I have been saying that the laws of physics are same. When I talked about homogeneity of time, I said the laws of physics are same, right? And what do I mean by this is that let's take Newtonian's case. In Newtonian's case, we consider sum of F is equal to, this is Newton's second law, is equal to ma, right? Now, this does not suffice to describe observations that are made by an accelerating observer, right? And so here we say that it's Newtonian's framework is incomplete and it's limited. So we need something else. But then we have this concept of action in physics. And so if you take action, that is S, right, as a fundamental definition of your theory, then it should be invariant. Then action is invariant, right? Now, the invariance of action actually implies something, that when you compute or you find the equations of motion, they are covariant. So it implies the covariance of equation of motion or equation of motions, right? Okay, so now let's finally talk about symmetry, right? Now we are going to talk about symmetry. Basically what this video is actually about, right? Now, symmetry is an incredibly powerful tool to simplify our calculations, right? Because if you say if something is symmetric, then you can simplify, you can, in layman's term, you can ignore some of the steps, and you can simplify your calculations actually, not ignore steps. Forget that I said that. You can simplify your calculations. However, symmetry also plays, in fact, a more fundamental role in determining the type of dynamics in certain physical theories, right? So symmetries tell you the type of dynamics of the system. Let me give you an example, right? You have special relativity. Special relativity is actually nothing more than a statement about the symmetries of physics on a particular space-time, and that's the flat space-time, right? Additionally, the fundamental interactions can be understood as arising from symmetry principles, and that's what you call the gauge invariance, right? Now, your very first exposure to symmetry was probably of the static type, right? So the static symmetry. That's how you were, in fact, I'm pretty sure that's how you were introduced to symmetries. Now, what that means is, I'll tell you, static symmetries are of, for example, you say you have a triangle, right? And you perform a rotation of 120 degrees, right? And the triangle remains the same, right? So that's your static symmetries. Now, the static symmetries are easy to visualize, right? You can think of a triangle, you could picture it in your mind, you could imagine how or what would happen if you rotate it by some angle, and you can picture all of this, and therefore it's easy to visualize. But what we are interested in are known as the dynamical symmetries. Dynamical symmetries. Now, an example of dynamical symmetries would be the Lagrangian, right? The Lagrangian of a system. Now, say you have a Lagrangian L, and you perform some transformation. So some transformation, and you get some L prime. But it happens as though that L prime is equal to L. And therefore we say that we call these type of symmetries dynamical symmetries, right? And of course, it's not as easy to visualize the Lagrangian obeying some symmetry than it was to visualize a triangle obeying a symmetry, right? But no matter what type of symmetry we consider, the spirit is the same. What I mean by that is, if we enact a transformation on something, and it will remain unchanged, or it looks the same, That's the essence, right, of a symmetry. Now, naively, it may even seem that our something that we're talking about must be only built out of things which themselves are invariant. And we build something out of these invariants and we get an invariant. However, if this were actually true, then it would be terribly restrictive, right? Because you're restricted now to choose what thing you want, and so that thing should itself be an invariant, or those things should be invariant, and then they would give you an invariant quantity. But fortunately for us, we can build an invariant something out of pieces that don't have to be invariant. And that is so long if we combine them in an appropriate way. And we are going to see all of this mathematically, right, later on. Let me, in fact, give you an example that we can build a rotationally invariant scalar from vector components, right? So if you have studied dot product, which of course you know about dot product, what is a dot product? It is building a rotationally invariant scalar from vector components, right? So you take dot product of two vectors and you get a scalar. And so that scalar is actually rotationally invariant, and therefore you're building an invariant out of things that are not invariant, right, by the operation of dot product. So dot product, that's why it's very useful for us, in fact. Right, now, so our preliminary focus will be on describing transformations, and then we will come back to making sure that they are indeed symmetries of the Lagrangian that we talked about, right? And we will do this part later, right? We will make sure that these symmetries are of the Lagrangian. We will do this part later on. First, our focus will be on describing transformations, right? Okay, so transformations come in various types. Now I'm going to list a long list. So yeah, and the types of transformations are global, or let me write these down over here. Types of transformations. Okay. And these types are, first we have, in fact, they're in no particular order. So let me just get rid of this one. We have global, we have local, we have discrete symmetries, we have continuous symmetries, we have finite symmetries, then we have, of course, infinite symmetries, and we have compact and non-compact. And we are going to look at these in detail, right? All of these symmetries that I'm listing over here. We are going to look with detail all of them, right? And we have internal and space-time symmetries. So these are all of the types of symmetries that we are going to be dealing with. Now, to clarify these words, global, local, discrete, continuous, and well, so on, these types of symmetries, we will look at static symmetry examples as that will be really helpful, right? Now, let's actually just start discussing these types of symmetries. So let's start with global versus local. Okay, now take an example for global versus local. Let's take an example 1. That is the transformation is that we translate each dot. Translate each dot. Now, for this, you have your system originally as you have one dot here, and another one here. Then you have one here, and one here. And let's actually draw one more row. So you have these 9 dots, right? And the global symmetry, or the global transformation, actually would be something that looks exactly the same, right? And so we would have now we are translating each of these dots. So this dot is corresponding to that, this dot is corresponding to this one, and the third dot over here is corresponding to this one, right? So you get the point, right? We are translating each dot in our original system that is over here. Now let me get rid of these funny lines so we can be more clear. Yeah, so now when we translate all of these dots in this manner, that is when we say that we have performed a global transformation, and the transformation was on translating these dots. And so you can clearly see that this part is symmetric, right? So if we performed global transformation, our system remained symmetric. However, there is another one that is local now. So if you perform a local transformation, that means that you translate each dot in a way that your system does not remain symmetric anymore. So to give you an example over here, it could be something like you translate one dot over here. This dot, you translate it somewhere over here, right? And then likewise you translate all of these dots in a very funny manner. That is the local transformation. And so over here you can see that your system is it's no more symmetric, so non-symmetric. Right? Now let's look at another example. In this case, we would have our transformation as the rotation of each circle in a plane. So for this, we take our system to be a set of these circles. I don't actually have to draw a lot of them, so this much would be fine. And you perform a global transformation. And now remember, your transformation in this example is what? It is rotation of each circle. So we are not translating, instead we are rotating circles over here. So if you perform a global transformation, it doesn't really matter, right, by what amount you rotate your circle, you're still going to get a circle. Now you can clearly see that this is symmetric. And even if you were to perform a local transformation, your circles, of course, it doesn't matter if you rotate one by 90 degrees, another one by 12 degrees. they are going to look the same, right? Because they're circles. So in this case, your local transformation is also symmetric, right? Now, a point over here to note is that if a system is symmetric under a local transformation, then it is automatically symmetric under a global transformation, right? So that is, if you can perform a local transformation and your system remains symmetric, then of course, if you perform a global transformation, that is for all of the points in your system, it is going to remain symmetric. But the inverse of this statement is not true. That is, if you were to say that you found out that your system is globally symmetric, it is not necessarily true that your system would be symmetric under a local transformation then, right? Okay, we talked a bit too much on this. Now let's talk about discrete versus continuous symmetries, right? Now, in this discrete versus continuous, we can also talk about finite versus infinite, right? And you will just see why. Okay, so take an example, actually example number 1 for this case. You have a triangle, right? And you perform a rotation of 120 degrees anti-clockwise, and you can see that the set of transformations for this are identity, that is E as in identity, right? And that would be if you make a complete rotation, right? And then you have rotation of this 120 degrees, and then you can even rotate it by 240 degrees. So these are the different types of rotations that you can perform on this triangle, and that is, if you were to label this sides of these triangles as A, B, C, so each side is different, and that's why you have this this set of transformations that you can do. If all of the sides were, say, same, labeled as A, then the only set you could form was of the identity. So, I mean, no matter how much you would rotate it by 120, I mean, in terms of 120 degrees, it would appear the same. And so that's why this is called finite rotation, right? Because there is a finite set of elements in this transformation set, right? Okay, now look at example number 2. Over here, consider you have a set of points that range from -infinity, and you have all these points, they go up to +infinity, right? And you have your transformation going from one point to another as some t1, and then from that point to some other point as t2, and likewise t3, t4, and up to infinity. Of course, then this is an infinite case, right? And that is obviously because the set that you could form for these transformations are t1, t2, t3, and up to infinity, right? So you could keep going on and on, right? Okay, so now let's talk about continuous symmetries, right? Over here we talked about these examples were for this discrete symmetries, right? This one. And in discrete, we were able to also talk about finite and infinite cases. In continuous symmetries, we will be able to talk about compact and non-compact cases. Right. So to understand this, consider an example, example number 1, that you have a circle and you perform some rotation on this circle by an angle theta. Now, know that this theta is limited to 0 to 2 pi, right? And if that is the case, then we have compact case, right? So that's the compact transformation. It's a continuous compact transformation. However, consider in an example number 2, if you were to have a continuous line, right, that's made by joining all those infinite points. So that continuous line, say it ranges from negative infinity to some positive infinity. You have this continuous line, and the transformation going from at one place on this line to another, it is some t sub d, where d, of course, because this line is an infinite line, belongs to negative infinity to infinity. And so if that is the case, if there is no limit to d, then we have non-compact. So it's a non-compact continuous transformation, right? Okay, so finally now the last one are the, let me go back, they're internal and space-time transformations, right? So let's talk about these. So we have space-time versus internal. Okay, so in this one, say if you were to give coordinates to the space-time, right? So if you were to coordinatize space-time, if that's even a word, then space-time transformations also change coordinates, right? If you transform space-time, then the coordinates also have to be transformed. However, on the other hand, internal transformations will do absolutely nothing to coordinates, right? And over here, let's give you some example of the space-time symmetries and the internal symmetries, right? So the example of space-time symmetry is special relativity. So it's SR, right? And for the internal symmetry, the forces that we have, the forces of nature, except for gravity, the strong force, the weak force, and the electromagnetic force. So all of these forces, they satisfy or they obey internal symmetries, while special relativity is associated with space-time symmetries, right? Now, we are going to have to deal then with the transformations, and we can do that mathematically, right? And how do we deal with transformations? We use the concepts of group theory and representation theory, right? Okay, so I have talked a lot about groups and representations, especially in my video on vector spaces. And so you could even go and watch them if you want to understand in depth about a group, right? But I will go over, from this point on, I'll go over groups and representations, right? Now, before I proceed further, I am doing all of this because all of this is extremely helpful in studying general relativity or just relativity itself. Because the idea of groups is very important, and using all of this representation theory, we are going to see where does that metric tensor appears, right? How does that metric tensor even comes in the game? We are going to see that using the representation theory. Okay, so now let's start with a group. A group G is a collection of transformations. So you have these transformations that would be A, for example, say B, C, and well, so on. All of these elements with a composition of this circle, right? And that could be any operation, multiplication, sum, or various kinds of operations, right? And it has to, that satisfies some of the features or properties, if you will. First one is closure. So if you were to say take some element A, B that belongs to the group G, and you were to take the composition of A and B, so A composition B, that should also belong to the group G. That's when it satisfies closure, right? Okay, and secondly, you have identity. So there has to exist an identity such that, let's say that there exists some identity E that belongs to the group G, such that when you take the composition E with A, it is same as if you were to take the composition of A with E, which is same as A itself. And this is, of course, for any or for all A that belongs to the group G. Then we have on C, the third one is the inverse. Now, for inverse, we say that for all element, say A, that belongs to G, there exists an A inverse that belongs to G, such that when you take the composition of A inverse and A, it is the same as if you were to take the composition of A inverse, if you were to take the composition of A and A inverse, and it gives you identity, right? That's inverse, so the inverse feature. And finally, we have associativity. I'm very bad with spellings, I guess. Right? Now, this one is, say you were to have some A and the composition, or A composition with some brackets, B composition C. So if you were to take this composition first and then compose that with A, it is the same as if you were to do this: A composition B composition C, right? And these are the features of a group, right? That's if you have something that is satisfying, a set that is satisfying all of these properties, that's when you call that set a group. Now, another thing you could do is think to add in perhaps commutativity, right? Commutativity, I don't know if I'm pronouncing that right, but that is, say if you were to have some composition A with B, you were to compose A with B, and if that is equal to B composition A, then you say that the group is abelian, right? And if this were not happening, then you would say that the group is non-abelian. Now, we don't have this as a feature of a group. So this does not have to be a feature of a group. We only need these A, B, C, and D as a feature of a group. Now, it is very important to also note that these B and C features that I written here, identity and inverse, these are very important features for formulating or for finding the invariants, right? Okay. Now, one more thing I would like to mention over here is that if you take a subset of elements of a group and they themselves also form a group, then the set of elements is called a subgroup of the original group. That is, say you have a group, some group G, right? And there are, well, some elements A, B, C, D, E, F. This is just an example, right? And say that the elements A, B, and C were also forming a group, right? So that is, they were satisfying all these properties A, B, C, and D, right? These properties. Then you could say that there is a subgroup. Say that is, actually I cannot use F because I used it over here. Let's just say there is a subgroup that is G prime, and that has these set of elements that are A, B, C. And then you call this G prime a subgroup of G, right? Okay, now again, subgroups must satisfy all of the features of a group. Now, we can abstractly specify a group. Say, for example, you have rotations in 2 dimensions with the composition being adding the rotation angles, right? But more often we think and calculate in terms of how group transformation acts on things, and these are what we call the representations of a group. So let me say this again, that oftenly it happens that we think and calculate in terms of how group transformation acts on things, and this is what we call the representation of a group. Now, I said representations, and yes, exactly, there are a lot of representations for a group. So a single group can have many representations. Some are even, in fact, more useful. And since they're useful, since they fully illustrate the contents of the group, and if that is so, if a representation is fully showing you all the contents of the group, that is what you call faithful representation. Now, let's consider an example, right? Shall we? So, say, consider a group G, and that is of the rotation, right? So there are rotations in a plane, so it's rotations in some plane by, say, 90 degrees, right? By 90 degrees, with the usual composition, that is of the addition of the angles, right? Now, this would have some representations, and these representations would be representation R1. Let's see, what would that be? You could represent it as the square having sides as labeled A, B, C, D. Now, this forms a group, and the elements of that group would be, remember first of all that we are performing rotations, and the composition is simply adding rotations, right? So if you rotate this say you rotate it 4 times with this angle 90 degree, you would get the same square back. So that's identity, right? Then you could simply just rotate it by 90 degrees, and so that is your element rotation by 90 degrees. Then you could again rotate this by 90 degrees more, and that would give you rotation by 180 degrees. And you could see that it wouldn't look the same as it is over here. It would only look the same if you rotate it 4 times. And that is because I have labeled these sides, right? And then you could perform another rotation that would be by 270 degrees. And if you were to perform rotation again with 90 degrees, so 90 plus 270 would be 360, and that would give you this identity, right? It would give you the same square back. So this is the set that we can form. And if you look at this set, this tells you all of the elements of the group. You will see that when I will show you more representations, right, for this example over here. And because it shows all of the contents of the group, then this is the faithful representation. Faithful representation. And this is actually indeed the only faithful representation for this example. So let's look at another representation, that is R2. And for this, we will in fact say that the sides, the difference is how I'm going to label the sides. So A, B, and then we will repeat these. So A, B. So only 2 of the sides are same. So we have A, and B, B, right? Okay, now the set that this could form for this operation and the composition, that is addition of angles, is then simply only if you were to rotate it by 180 degrees, you would get the same thing back, and that is identity. Or you could rotate it by 90 degrees, right? And so these are only the 2 different transformations that you could do that would leave this square appearing different. But because you see we have these repeating labels, then we say that this is actually a degenerate representation, right? And we could have another one, and this is the last one that we could have, and that is representation R3, where you have all the sides of the square labeled as A. So all the sides are same. And so if that is the case, then the only set that we can form is of the identity, right? And then this would be highly degenerate identity representation. So again, it's a degenerate but highly degenerate identity representation. And so you could see now that the only faithful representation was this one, right? Because over here we had all of the elements of the group, but in the second one we did not have R180 and R270, right? And in the third one we only have E, right? Okay, so moving on, we often work with representations where the transformations act linearly using matrices, right? So then consider an example. If I were to do something like this, right? Let me just do it. I have this square and say these sides A, B, C, D, right? I could give this a matrix that is 1, 0, 0, 0 when I have done nothing to this square, right? Now you say I rotate this, right, in such a way that I have A over here, B, C, D, right? And say that I give a matrix, a column matrix as 0, 1, 0, 0, right? And likewise, I perform another rotation that causes the labels to shift like this, and this I say it is 0, 0, 1, 0. So all I'm doing is bringing this one down one by one, right? So you get it? Okay, so and then finally we would have something like A, D, and B, C, right? And say you give this a column matrix, you define it by 0, 0, 0, 1. Okay, then you could define your rotations and identity matrix using these set of column matrices. And then what you could do is you would have your identity matrix is represented as simply 1, diagonals are 1, and everywhere else you have 0. And your because we are performing rotations with 90 degrees, so our 90 can then be represented by, again I'm using these column matrices, so we did our rotation with 90 degrees in this square, and so the matrix that we can form is 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0, right? And likewise you can form a matrix for 90-degree rotation that would be 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0. Okay, and then you can have R240, so rotation by 240 degrees. That matrix would be 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0. Right? Okay, now all these matrices, they are going to behave as expected, right? So what I mean by that is R90 and then R180, this would be the same as R270, right? So if you perform a rotation by R180 first and then by R90, 90 degrees, that would be the same as if you were to perform a rotation with 270 degrees, and etc. Right? Now note that this all of these elements, they form an abelian group, right? And that is because of the fact that if you have any of these rotations R and R prime, so you take any other one, that is the same as if you were to take the other one first and then the first one, right? So that is, if you were to take consider this example, if I were to shift this, so if I were to do R180 and then R90, actually I'm sorry, we act them like this, right? So in this example, I am doing R180 and then I'm doing R90. However, in this one, I'm doing R90 and then R180. And so this would still give me R270. That simply means that the group is abelian, right? Okay. Now, there was everything that I did at the end of this video is mostly abstract, right? And so I don't know if you enjoyed it as much, but in the next lecture, things are going to get really interesting, because there I will actually focus on symmetry transformations and the metric, right? So the metric will appear over there. We will also learn on how to build an invariant and talk some more on representations, and we are going to introduce dual representations and the relation between these two, that is the representations and dual representations, is very important, because that is what will tell us something about the metric that we use in special relativity and general relativity. So if you can recall, it is something like one. If you were to take one coordinate, that is either space or time, as positive, then you were supposed to take all the others negative, right? So for example, if I took time coordinate as positive, then all the space coordinates are negative. And of course, everywhere else we have 0. At the diagonals, it's like this. So we will see how does this appear, right? And it would come purely out of representations and dual representations.